Hello. So far in this course, we have discussed about the structure of solid, the crystal structure, the basis, the lattice, and how the combination of basis and lattice makes a complete crystal in infinite space. But we did not consider what binds those atoms in the crystal together. So here we will discuss about that. What is the binding force of the atoms that makes a crystal? You are familiar with ionic bonds, covalent bonds, but now let us discuss something interesting. So, if we consider inert gases, if we have very low temperature and high pressure, they can be formed into solids. How? They do not have any ionic force between the atoms. They do not have any covalent interaction as well. In case of inert gases, the outermost shell is completely full. So, they are not supposed to interact with each other in any way, and if they do not interact, how do they form a solid at all? So, they must interact, and here we will discuss about different kind of interactions that binds the solid together. Nuclei, as we know, repel each other, and there are electrons around it. That electron cloud also repels each other. Nuclei attract the electron cloud, and the electron cloud also attracts the nuclei. And this must be the main form of binding in crystal. There is very little contribution from magnetic forces, if at all they exist in a solid. Not every solid is magnetic. There are few solids that are magnetic, and the magnetic interaction plays a very tiny role. The gravitational interaction between atoms have no role in crystal binding, that can be purely neglected. Now, let us consider the case of the crystal of inert gases. The inert gases form the simplest crystals. The distribution of electron is similar to that of free atoms. So, they do not have any electron sharing or ionization or anything like that. The crystals are very weakly bound, just because the interaction must not be strong in that kind of a situation, but there is some kind of interaction. And because of that weak binding, it has very low melting temperature, and all the inert gas crystals are transparent insulating solids. The atoms have very high ionization energies, and the outermost electron shell are completely filled. That must be the case, and we can see that the atoms are packed together in the closest possible way. Helium 3, helium 4, these have HCP structure, and everything else have FCC structure. You have calculated packing fractions, and you now know that these are the closest possible binding. So, what holds these atoms, the inert gas atoms, together? Let us discuss about van der Waals interaction. So, what is it? What kind of interaction it can be? If you consider two identical atoms of inert gas, at the core of that atom there is a nucleus, and surrounding is an electron cloud. If you consider the example of helium, there is only s electrons. So, it is completely, the electron distribution is completely spherically symmetric, and if this arrangement is there, then you have learnt from electrostatics that a spherically symmetric charge distribution, its electric potential behaves as if the entire charge is located at the center of sphere. That means, you can, as far as electrostatics is concerned, you can consider that the nucleus, the positive charge is located at the center of the atom, the negative charge of that electron, that is also located at the center of the atom. So, there is no charge, and if there is no charge from an atom, it cannot have any electric interaction, electrostatic interaction. Then what happens? Then there can still be dipolar interaction if these two charge centers do not overlap, if they are allowed some fluctuation, some oscillation, something like that. So, oscillating dipoles can give us some understanding of this. Let us consider that kind of a situation. As a model, let us consider two identical linear harmonic oscillators, and we will consider that they are separated by a distance r, capital R. So, I am drawing one atom, one dipole here. This is the positive charge center and this is the negative charge center. Another dipole here, positive charge center, negative charge center, and let us assume that these are connected by a spring, so that we can use the spring constant in our Hamiltonian. So, they are certainly not connected by spring, but we are just thinking that the force between the positive and negative charge centers, they interact with each other like a spring kind of a potential. We consider the distance between the positive and negative charge centers here as x1, here it is x2, and the separation between them is given as capital R. So, how much is capital R? This much. This is capital R. So, this is our first oscillator and this is our second oscillator that we have considered. Now, each oscillator bears charges, that is plus minus E, plus E here minus E here, with separation x1 and x2. The dipoles oscillate along the x direction in one dimension, we have considered for simplicity. Now, if we consider that P1 and P2 are the momenta. So, let me write it here, P1 is the momentum for this oscillator, P2 is the momentum for this oscillator, and if C is the force constant corresponding to the spring and we consider identical atoms. So, it is the same force constant, similar kind of springs, same force constant. We can write the Hamiltonian of the unperturbed system, that is, there are two such oscillating dipoles and they are not interacting between each other. Without any interaction, if we try to write the Hamiltonian that we call the unperturbed Hamiltonian, denoted as H naught, can be written as, their mass is also identical. So, I am writing m for the mass, half 1 over 2 m P1 squared plus 1 over 2 m P2 squared plus half C x1 squared, this is the spring potential, plus half C x2 squared, this is also the spring potential from the other dipole. Now, each coupled oscillator is assumed to have the frequency omega naught. What is omega naught? If we shine light on these atoms individually, the charge centers would oscillate about each other as a result of the light. So, there may be different frequencies, we are considering the strongest optical absorption line, that is the resonance frequency for this atom, and that resonance frequency is omega naught. If that is the case, that means that is the characteristic of this spring. So, we can write that the spring constant C is m omega naught squared. This is the resonance condition for the strongest absorption line, optical absorption line for this atom. And now, if we consider Coulomb interaction, so what allows us to consider any Coulomb interaction? If we see that the charge, positive charge center and negative charge center, these are separated now in this kind of a situation, then there would be Coulomb interaction. And the Coulomb interaction can, the Hamiltonian, the corresponding to Coulomb interaction can be represented as H1, and that can be given as E squared over R plus E squared over R plus x1 minus x2 minus E squared over R plus x1 minus E squared over R minus x2. So, let us go back to the picture. The positive terms are repulsive term, that means that is between the positive and positive charge center, and the negative and negative charge center. The negative terms are attractive terms between the positive and negative charge center here, and the negative and positive charge center here. Now, this Hamiltonian is written in CGS unit. In SI unit, it will have some change, some dressing would be different, but the physics will remain the same. And we have already discussed that x1, the absolute value of x1 and absolute value of x2, that is the difference, the distance between two charge centers, this is much less than capital R, the interatomic distance. This assumption is a very good assumption, excellent assumption. This will be valid for every kind of solid. And within this assumption, we can write H1 nearly equals minus twice E squared x1 x2 over R cubed. It will be a homework for you to show this, that within this assumption we can reduce H1 to this approximate form. Now, once we have considered this approximate form, the total Hamiltonian with the approximate form of H1, if we write H naught plus H1 now and H1 in this approximate form, we can diagonalize it and find the normal modes, where XS, the symmetric mode, that can be represented as 1 over square root 2 x1 plus x2, and the antisymmetric mode XA, it can be given as 1 over square root 2 x1 minus x2. Showing this is a homework for you. You are supposed to consider, you are supposed to add this form of H1 with H naught from the previous page and diagonalize that Hamiltonian. If you diagonalize that Hamiltonian, you can use softwares like Mathematica, MATLAB or whatever you wish, or you can do it analytically also. This is not a big Hamiltonian. You should get the symmetric for the symmetric normal mode you should get this form, and for the antisymmetric normal mode you should get this form. Now, if we solve for x1 and x2, we can write down x1 in terms of xs and xa equals 1 over square root 2 xs plus xa. Similarly, x2 would be 1 over square root 2 xs minus xa. So, if we now write the symmetric and antisymmetric momenta Ps and Pa, in terms of Ps and Pa, we can write P1 equals very similarly square root 2 Ps plus Pa, and P2 would be given as 1 over square root 2 Ps minus Pa. The total Hamiltonian after these transformations can be represented using the normal mode coordinates and the normal mode momenta as H equals 1 over twice m Ps squared plus half C minus 2e squared over r cubed xs squared plus 1 over twice m Pa squared plus half C plus twice e squared over r cubed xa squared. This is the total Hamiltonian in terms of normal mode coordinates and normal mode momenta. Once we have that, the normal mode frequencies may be evaluated. The normal mode frequency in this case, if we write that as omega, can be written as C plus minus twice e squared over r cubed divided by m square root of this entire quantity, and this can be represented as omega naught times 1 plus minus half times 2e squared over cr cubed minus 1 over 8 2e squared over cr cubed square plus more higher order terms. So, what is omega naught here? Omega naught, as we have represented earlier, is C over m square root of this, and we have obtained this expansion just by expanding the square root. Why did we do that? That will be clear soon. Here in this square root, we cannot perform few operations that for which we will need this. Now, let us consider the 0 point energy for this coupled oscillating system. In case of classical oscillators, we have no 0 point energy. but here these are quantum oscillators. So, it cannot have absolute zero energy, it will have certain energy even at the lowest possibility. So, the lowest possible energy is non-zero in this case. And how do we obtain the 0 point energy? The 0 point energy for this system would be given as half h cross omega s plus omega a. This comes from the plus minus sign here and here. So, this gives us the 0 point energy of this coupled oscillator system. Because the interaction, because of this interaction that we have, the sum is less than the uncoupled value of 0 point energy. If we did not have any coupling between the two oscillators, if we consider no coupling, then we have the 0 point energy for each oscillator given as half h cross omega naught and multiply it with 2, because there are two oscillators, this will be the total 0 point energy. Here the 0 point energy is less just because these two oscillators are interacting. Now, if we consider the difference between the 0 point energies, that is delta u, that would be the cohesion, that would be the cohesive energy. That is given as half h cross delta omega s plus delta omega a. In order to find out delta omega s and delta omega a, this expansion here, this would be of enormous importance. Using this expansion, we can write down the delta expression for delta u as minus h cross omega naught times 1 over 8 2e squared over CR cubed square of this, and that means we have 1 over r power 6 kind of dependence and the rest are just a constant. So, it can be written as minus a over r power 6, where a is a positive constant. So, with a minus sign, this is an attractive interaction, you can clearly see, and this is attractive just because this 0 point energy of the coupled oscillator is less than the 0 point energy of the oscillator without considering any coupling. That is the reason that this difference, this energy that we have found here is attractive, and it goes as, this attractive energy goes as r power minus 6. This is the leading attractive term. Of course, if you take this expansion a bit further, you will get more attractive terms, but their contributions would be much less than this term. This kind of interaction is called the van der Waals interaction. It also has other names like London interaction, or simply the dipole-dipole interaction. Note something interesting. If we had classical mechanics in our mind, we couldn't have derived any such interaction, because we derived this interaction by considering the difference between the 0 point energies in case of interacting and non-interacting system. In case of classical system, there is no 0 point energy, and if there is no 0 point energy, there is no difference as well. So, this interaction energy, that is the van der Waals interaction energy that we have calculated now, has purely quantum origin. There is no classical analog to this kind of interaction.